25 years ago, this is what the small Hawaiian community of Kalapana looked like. Lush, green and vibrant, it was home to 3,500 people.
And this is what it looks like now. In tonight's show, we're going to show you what happened here and explain why our planet is just so active.
This is Volcano Live. Welcome to Hawaii, welcome to Volcano Live. We are in Kalapana on the southeastern flank of the Kilauea volcano, which has been our home for the last 3 nights. It is the most active volcano in the world, and here you can really see the devastation that it has wreaked in the last few years.
In 1990, a lava flow from the East Rift of Kilauea came down and took out a community here. But amazingly, people are coming back and building their houses.
They are, and we're going to be meeting someone in just a bit who has made that choice, who is rebuilding their home in this desolate landscape. But first, let's see what else is coming up on today's programme. Tonight, I take a Jules Verne-style adventure right into the centre of the Earth.
Above ground, I explore the links between eruptions and earthquakes.
Over in the Caribbean, a team of volcanologists turn to violence, but all in the name of science.
And Ed Byrne discovers what turns an innocuous wave into a deadly tsunami.
Lots to look forward to, and you can contact us throughout the programme by going to our website, bbc.co.uk/Volcano Live, or you can tweet us on #Volcano Live. Now let's just give you a little bit of a reminder where we are. We are right in the middle of the Pacific Ocean, the island chain, the archipelago of Hawaii, and we are on that big island at the bottom. Now yesterday we were at the site of the 1969 eruption on Mauna Ulu, another part of the Kilauea volcano. After the show we packed up and moved down here to the coast. It's quite warm here. We've got used to being rather cold and up in the kind of mountain mist, but now we're on the balmy coastline. Yeah,
and we keep on talking about Kilauea being the most active volcano in the world, and the reason for that is in 1983 lava started pouring out from the East Rift, which is over there. And that whole escarpment, you can see it running along there. Along the ridge is a line of fissures and craters, and that's where the lava came out of. Now, down here, that lava is cold. We can walk on it fine. But if you go across just to the foot of that slope, as me and Kate did the other day in the helicopter, you can see there's a lot of red stuff coming out.
Now there's you can see the scale of it. It almost looks like a kind of lava ocean, doesn't it?
And every so often you get what they call breakouts. You get these rivers coming down. In other places, little skylights, we get that hint of magma flowing underneath.
And it is an extraordinary sight to think that what looks like a dead landscape, a landscape that has been active and is no longer active, suddenly there are these little points which remind you just of the force of this volcano.
No, absolutely. And it's always quite hard to get an idea of how volcanoes move, isn't it? That slow creeping across the landscape.
Yeah, so we've got our time-lapse cameras have been set up right at the lava edge over there. You can see how it really does creep in this quite insidious way, doesn't it?
It's addictive watching it though. It's kind of hypnotic, isn't it?
It really is. It's a sort of a beautiful movement. But as you said yesterday, not a killer because it's so slow.
No, that's right. But the thing is, it's so hot. I mean, you can't get a feeling of how hot it is unless you look at it at night. And at night, you just get that creeping lava, and you can see, when you see this, you can see that it starts to fire off, little bits of vegetation starts to burn. So those temperatures are easily 500, maybe even 700 degrees.
It is a spectacular sight. Less spectacular probably if you were one of the people who were living in Kalapana when the lava flows started heading this way. Now we've got some extraordinary footage of the day that the lava crept towards this community, and as you can see, I mean, it was a slow creep. People were were able to rescue their possessions. They were able to even move buildings. That's the church.
The church moving, it's extraordinary.
And that's now about 5 miles down the road. But what a lot of people weren't able to do was obviously to move their houses, and the inevitable happened.
Well, but what we must emphasise, absolutely no one was killed in that eruption, but it did leave something like 180 houses destroyed. Many of them, I mean, sadly, underneath this lava. It's what's slightly eerie walking here is knowing that there's people's homes. And there's things like, every so often you get this detritus of homes.
You do. I mean, you see, if you walk around the lava here, and we've got some shots of it, you can see what looks like people have just dumped rubbish. They haven't at all. The furniture that you can see, the bathtub, you know, those are actually entombed in lava. Look at that car
there.
Is
extraordinary. That's one of the iconic images of this
It's a
place.
real sort of reminder that this was once a vibrant community, and you would think that now it would be completely deserted, but that's not the case, because just over there you can see that there are houses back being built on the lava. Now that does seem to be an extraordinary, well, a madness really. Well, one of the people who has moved back to Kalapana is Robert McKnight. Good morning, Robert.
Good morning.
Lovely to see you. Thank you for joining us today.
Thank you. You're welcome.
So can you tell me when you moved here for the first time?
Well, I moved out here on the lava about 2005 or 5, I think it was, yeah.
So there had already been lava flows. The very destructive lava flows that we saw in that earlier film had already happened.
Yes, yes.
So you made a conscious decision to move to a place that had already been wiped out by a volcanic eruption.
Yes, I did.
Now you laugh about that, and actually we've had questions about people like you. I mean, you're not unique. There are plenty of people the world over who live in the shadow of volcanoes. One of our viewers, John Lycett from Cannock in Staffordshire, said, why do people insist in living near volcanoes even though they know the dangers? Why did you decide to move here?
Well, I think the biggest reason was the openness of the area. Mm-hmm. It lacked mosquitoes and coquet frogs, so that was something that was allergic to mosquitoes. And probably one of the most important factors for me was an opportunity to get oceanfront land that was very reasonable in price and still just beautifully expansive. And the weather is great out here. The small issue of lava covering me was put in the background, and
I mean, did you slightly think it's happened already, it probably won't happen again? Was that sort of in the back of your mind?
I did. It was actually pouring out there a few miles past my house into the ocean. I just felt that the width of the lava pouring down the mountainside would be a high chance of running me over again. But lo and behold, you know, the Pu'uo'o vents shut down from an earthquake and moved eastward a few miles, and sure enough, it came down the hillside and went right next to my house and eventually took the house.
So at that point, I mean, can you describe how it feels? You know, for us, we live in a very benign country. You know, in England, we don't have any volcanic eruptions. How does it feel to witness that very slow creep of lava towards the thing that you've built with your own hands? I mean, you must have felt very emotional at that moment.
I was, and reflecting maybe on people that were here 15 or 20 years earlier that had a lot of green vegetation in homes. They watched the pulsing of the lava coming and stopping and coming. It's torturous because it just may or may not take your place. So there's a lot of waiting. It certainly interrupts one's life completely. And it's painful no matter what, to see one's own house, you know, go up in flames and get covered.
But I suppose that then makes your decision to come back even more extraordinary, because you lost your home, all those years of work building it. You'd come, as you say, to your bit of paradise, and yet, if we look, we've got a camera, I think, just over there. You are rebuilding again. Are you just a glutton for punishment, Robert?
I hope not. Well, there were financial choices, of course, too. I couldn't hop on a jet and go where I wanted to. So it left me, unfortunately, without the assets to do much with. And that property, once again, was inexpensive, less expensive than my oceanfront.
I mean, I'm slightly surprised you have to pay for it at all, and they're
Yeah,
not just
well,
giving it away.
that's some people feel that way and don't want to live here, but those of us that do, it is just a wonderful atmosphere if you're not looking at lava coming at you. Unfortunately, for my second place that I quickly got to have a place to live in, actually, after losing my actual house, the lava, after 2 years' time, wound up 300 feet off of my doorstep again, and I was looking out at a very real threat of the lava covering me. My house wasn't, again, finished at the time, but that was you know, a very terrible feeling that I just can't have that happen to me twice. And it subsided, actually has moved back to where it had been years before, so I get a little reprieve. At least to get my house finished and insurance on it this time, I won't have the financial losses, you know, just kind of the emotional, but, you know, if there's compensation.
But how would you describe the community that do live here? Do you think, are you kind of pioneers? How do you describe yourselves?
I don't know. Everyone out on the lava, I think, is looking for, you know, the nice weather, and it is the expense. You know, homes were getting very expensive a few years back, and for the average person, it's stressful to find, you know, their paradise in Hawaii. So people that are out here on the lava can enjoy all the amenities of living in Hawaii, but, you know, the real estate itself is affordable.
And kind of unique.
And very unique also. So there are a lot of pluses here, and everyone that does live out here in these communities now really do appreciate being out here. They really like being out here.
Well, Robert, it is a very special place. I wish you all the luck, and I hope the lava stays at a good safe distance.
Thank you very much.
Thanks for joining us. Thank you.
You're welcome. Bye.
So it is perhaps surprising that people like Robert choose to live in areas of the world that are geologically volatile, and it's particularly, as Ian explains now, because science absolutely knows where those areas are and what makes them so explosive.
I've come to the Bay of Naples to see what is for me the most important Roman ruin in the whole of Italy.
There she is. I know it doesn't seem like much, does it? Sandwiched between all these kind of modern apartments and restaurants and right beside this busy road, but this is a really special place.
This is a temple of Serapis, just a stone's throw from the sea. It's not actually a temple at all. It was a Roman marketplace, built around 2,000 years ago.
But it's still a kind of temple for geologists because of this book, Charles Lyell's Principles of Geology, first published in 1830. This book is the cornerstone of modern geology. And right here, embossed in gold in the front, the Temple of Serapis.
This place changed the way Lyell looked at the world. Not because of the ruins themselves, but because of the tiny holes that pockmarked the 3 marble pillars.
Crucially, Lyell recognised this as something you commonly find on the piers and moorings around here. It's formed by a type of clam, Lithodomus lithophaga, a tiny sea creature that nibbles its way into stone.
Lyell knew that the Romans originally built this structure on dry land, but the holes in the pillars meant that at some point it must have been submerged under the sea, only to rise back up again.
This observation was pivotal. It convinced Lyell that the Earth's surface wasn't static, it was constantly moving, constantly changing. And what's more, those processes are still going on today. They can be observed all around us. That principle is the foundation on which modern geology rests.
Today, geologists have a theory to explain Lyell's observations. It's the theory of plate tectonics. It says that our planet's surface isn't a single solid shell. It's broken into lots of different pieces, or plates, like a giant jigsaw. And those plates are constantly moving. the boundary between two of those plates runs right the way through Italy.
Here in the Bay of Naples, I'm on the Eurasian plate, which is more or less stationary in contrast to the African plate, which is over there to the south. And it's heading northwards at a few centimetres a year, shunting into the Eurasian plate. So effectively, the two plates have collided.
And because the African plate is denser, it slides beneath the Eurasian plate. This is known as subduction.
If I show you how it happens, this is the Eurasian plate here, put an E. And this is the African plate that comes down and subducts below it. So there's Africa, and that's moving in that direction there. As that slab descends deeper into the mantle, the temperatures get hotter and the pressures get higher. Now down there, hundreds of kilometres below the surface, inside the plate, and locked away in minerals in the rock, there's water. Water that, under that hot pressure cooker environment, gets forced out. And the reason that that's important is that the water reduces the melting temperature of the mantle rocks, turning solid rock into magma. Magma that pools and rises up through cracks and fractures in the crust to erupt out as a volcano.
The Temple of Serapis and this whole area is right above the subducting plate. Beneath the ground lies a huge pool of magma. And you don't have to go far from the temple ruins to find evidence of it. Just a kilometre down the road, hot gases seeping up from the furnace below have created this alien landscape.
The subduction of the African plate beneath the Eurasian plate allowed magma that originated deep within the earth to rise up towards the surface. Now huge quantities of magma have pooled in a vast chamber just 10 kilometres beneath my feet.
Sulphuric gases paint the rocks yellow, and water that's been heated to boiling point underground billows out as steam. As the pressure in the magma chamber rises and falls, the land in this area heaves upwards and then sinks back down. That's why, over time, the Temple of Serapis, which was originally built on the shoreline, has found itself periodically submerged beneath the sea. And the magma chamber beneath the ground here is just one of a whole string along this plate boundary. The same subducting plate produces the magma that fuels all of Italy's famous volcanoes like Etna, Stromboli and Vesuvius. In fact, subducting plate boundaries like this one are responsible for 80% of all the volcanoes on the planet. Volcanoes are like beacons, marking out the places where these shifting plates collide. But they're not the only evidence that the surface of our planet is constantly on the move.
Plates are the rigid skin of the earth, the terra firma on which we live. And because the plates are constantly moving, when one continent-sized slab of rock grinds into another, tremendous pressures build up. Enough pressure for that brittle crust to snap and break. And when that happens, you get earthquakes.
Another earthquake has struck northern Italy, killing at least 15 people and burying several others under rubble.
Just 8 weeks ago, the same subducting plate boundary that produces Italy's majestic volcanoes caused a series of lethal earthquakes near the city of Bologna. And just over a year ago, subducting plates beneath the Pacific Ocean caused the massive earthquake, which in turn triggered the tsunami that devastated the coast of Japan. 75% of all the world's earthquakes are caused by subducting plate boundaries.
Plate tectonics is driven by internal heat escaping from the depths of the planet. And with that comes earthquakes and volcanoes. And there's no better evidence that Earth is a dynamic, active place, changing all the time, sometimes violently. It may seem to us humans that the ground on which we stand is fixed, but it's actually constantly on the move, just as Charles Lyell predicted. A point that comes out of that film is the fact that we've known for a couple of centuries now that the land moves in earthquakes and volcanoes, but it's only in the last 50 years we know where the plates are. We've got a map of them here showing all the major plates. So all of these are those rigid blocks that are jostling around, and you can see them there. Now, what we can do is we can put on all of the known volcanoes. So there's about 1,600 ones that have been erupted over the last million years or so.
And it's very obvious, as soon as you look at this, that the majority of them run along coastlines, along the coast of North America, South America.
Through the Med, around here, and into the ring, this part of the Ring of Fire. Now, the point really is that a lot of these volcanoes occur at the coast, at the junction between the continent and the oceans, and that's where subduction zones are. That's where the ocean plates are sinking, getting forced, particularly under the continental ones, and they're disappearing down there and creating these subduction zone volcanoes.
Should we have a look at our map? These are the volcanoes that have been active in the last 24 hours. And again, they map, really, the majority of them are in those subduction zones. And these are the nasty volcanoes, aren't they? I mean, these are the dangerous ones.
These are the dangerous ones. And the reason for that is that the ocean plates, as it pushes down here, in the film I was explaining how the magma melts, rises up and punctures its way through.
Yeah.
As it rises through the continent, it picks up all sorts of minerals from the continent, and that makes the magma sticky.
Right.
The point there is it traps gases in there, gases that pent up pressure, and when they get to the surface around here, they just explode out. So those are the real killers.
Now, of course, the other thing that causes us human beings to notice that our planet is as dynamic as it is earthquakes. But is there any sort of correlation between earthquakes and volcanic explosions? Well, let's have a look at where the latest earthquakes have been. These are all these green circles here are all the earthquakes that have happened in the last 24 hours that are over 0.2 or 0.3 of magnitude.
Magnitude 2.
0.2.
And the size of the circles relates to the size. So this is the biggest one. It's a 5.2 down in Papua New Guinea. Not very much for Papua New Guinea, has to be said. If it happened in Britain, it would be one of our biggest ones ever. But the point is, exactly, they occur along the plate boundaries. Volcanoes will occur along the plate boundaries. They're intimately related.
And the other thing, if you think about the population centres, I mean, if you thought about the number of people who live along that coast of America and indeed South America,
Southeast Asia, around here,
Southeast Asia in particular. So it's not just the people of Kalapana who insist on coming back to a volcanically active area. It seems to be something that people the world over do. And it was a couple of those particularly densely populated areas in Southeast Asia and Japan that were so devastatingly affected by the tsunamis in 2004 and then in 2011. Ed Byrne went to investigate how an earthquake can trigger one of these deadly waves.
Over the last decade alone, powerful earthquakes and the immense tsunamis caused by them have killed over 800,000 people. Dr. Tiziano Rossetto from UCL is one of the UK's leading seismologists. She's set up an experiment to show how the build-up of pressure is the primary cause behind all earthquakes.
These are our tectonic plates then?
Yeah, this is an example of where the plates are moving together against each other. There's friction at their interface, which is locking them together. And the stress builds up over what can be decades or even hundreds of years. And as the energy increases and increases, hopefully we'll see the time of the earthquake.
Hey. Ooh. And they just popped.
So that's the earthquake that's happened, and the energy that's built up over hundreds of years is released in seconds, and that's what generates the seismic waves that cause earthquakes.
And that type of earthquake we just demonstrated there, that's what type would you call that?
These are subduction events. This is the sort of thing that happened that triggered the Indian Ocean tsunami in Sumatra. The two parts of the crust are moving together, and one plate can go below the other. But they interlock, so the top plate is being dragged down as well. And when the earthquake happens, you have the spring back of the top plate, which is causing the movement of water above that generates a tsunami.
The 2004 Boxing Day tsunami was formed just over 100 miles off the Indonesian coast when a subduction earthquake triggered a massive displacement of water above it. The wave it created travelled at the speed of a jet plane, yet was only a metre or so high. So how did such a small wave turn into the immense wall of water which killed over 220,000 people? I'm meeting earthquake specialist Dr. Adam Crew from Bristol University to find out.
This is Tim, and he's going to help us show what happens when the tsunami actually hits the shoreline.
Hello, Tim. So you can see, right, it's not that high, and then...
Going down there, it breaks.
You've got a massive amount of water there travelling at speed. What is it that causes it to break just there on the shore?
Well, we were moving so much water up there, very, very deep deep wave, and that was going quite fast. As the waves get closer to the shoreline, they actually start slowing down because the water gets shallower. So round about here, the front of the wave was slowing down, the back kept going, and it meant the water builds up.
So the back of the wave catches up with the front of the wave, and that forces the water up.
As it gets high enough, it starts breaking. But then tsunamis are unusual because they're also very long waves. So once you've got them, the water hits the shoreline and it keeps going. So it is not like a normal wave on the beach where
Which breaks and then flows back out again.
Flows back. This one keeps going, and that's why they cause so much damage.
So I understand how a subduction earthquake at sea can displace water and cause a tsunami. But what makes earthquakes so destructive on land? Well, it's all to do with waves of a different kind. Seismic waves.
There are two different types of seismic waves that get generated at the time of an earthquake. The first one, the primary waves, travel like pulses in the ground, essentially through compression, and they're very much like sound waves travel through the air. The second type of wave travels sideways.
Or you mean like a lateral, a side-to-side movement causes the wave to go
forward? Yeah,
forward.
that's right.
Yeah.
Both primary and secondary waves bounce off or interact with the surface, and they set up new waves called surface waves, which are the ones that actually cause a destruction.
So if I wanted to see these so-called primary and secondary waves, or P and S waves, and the surface waves in action, where better than the country's biggest earthquake simulator? Adam explains that one of the ways to measure these seismic waves is using a magnitude scale like the Richter scale.
The Richter scale is surprisingly complicated, isn't it?
It's a logarithmic scale. If you start at, for example, 2, the jump to 3 is 30 times more energy.
Right.
So 30 times more powerful, the earthquake. When we go up to 4, that's another 30 times more powerful. So a magnitude 4 earthquake is about 900 times stronger than the magnitude 2. We're going to start with a really small sort of British earthquake, sort of magnitude 3 on the Richter scale. Headed into a European earthquake. That's headed closer towards the 6. The sort of thing they would get down in Greece, Portugal, Italy.
Your P waves and your S waves coming together to form these seismic surface waves.
Absolutely.
See, I've been listening.
And then onto the big sort of Japanese American earthquakes.
How long would they normally last in real life? How long does an earthquake of this magnitude last?
These large ones could go on for 2 or 3 minutes.
Really?
So this is the sort of thing we would keep saying, oh, yeah, that one only lasted a minute, but you could get 3 or 4 minutes of that.
So today I've learned that earthquakes come in all shapes, sizes, colours and flavours.
Subduction faults under the sea can cause incredibly destructive tsunamis, while on land it's seismic waves which do all the damage.
Now, Hawaii sits in right slap bang in the middle of the Pacific Plate, which means that it's in the fire line for all those subduction zone earthquakes in Japan, in Chile, Alaska and the like. And right in the middle is this set of islands. In 1946, Hilo, the main town on Big Island, suffered a real tragic tsunami disaster. This is the 1946 tsunami, which sweeps in. You can see a surge of water coming in to the harbour town now. 96 people lost their lives, but as often is the case, these kind of tragedies are the kind of impetus for doing something about it. And I've got Dr. Gerard Fry here from the Pacific Tsunami Warning System, which was essentially set up on the back of that tragedy, wasn't it?
That's right, yeah. We started operating 2 years later.
So what's the remit of the organisation?
Basically, we provide warnings, tsunami warnings to the entire Pacific and also the Indian Ocean and the Caribbean. And the way we operate is basically we're looking for earthquakes. And the worldwide seismographic network, we get all of that data in real time. So we can issue a warning within about 10 or 11 minutes of any earthquake anywhere on Earth.
That's pretty extraordinary. Now, you've been closely, but the last big one was the Japan one, 2011, and you've worked closely on that, haven't you?
That earthquake, we knew about it 40 seconds later. Seismometers in Japan transferred to us, and then we got paged. The Japan Meteorological Agency, they were very fast in issuing a warning. They got a warning out in 2 minutes and 40 seconds. the earthquake itself actually lasted 3 minutes. So they, unfortunately, they underestimated the magnitude of the earthquake, which is part of their tragedy. We took a little longer. We issued our warning at 9 minutes.
And we get some footage of the modelling of what that tsunami did. This is quite extraordinary. So this is the wave coming out, or set of waves really, and the heights are in here in colours, about a metre high amplitude in the ocean.
That's right. And so that was Japan. Here are the Hawaiian Islands. We're now about 6 hours into it. The tsunami hit the Hawaiian Islands at about 7 hours. And went on, and you'll notice behind the leading waves there are waves reflected, so the ocean is just oscillating.
And of course, although it's a few tens of metres, a metre in the ocean, it's when it gets into the shallow zones of the coast that it really rears
Right,
up.
the waves slow down in shallow water, and to carry the same amount of energy they have to grow in height, and they'll grow by a factor of 4 or 5.
It's extraordinary. How much time did it take to start hitting South America?
It took 22 hours to get to South America, but you'll see that the waves are still big, and in fact Talcahuano in southern Chile was hit by waves 2.5 meters high. Significant damage, boats picked up, carried into the town. And now we see the tsunami sort of getting through the Drake Passage and into the South Atlantic. These waves are very small.
Outside of Japan, how many people were killed by this tsunami?
Well, the warning system worked. There were 2 deaths. There was one in California, a photographer who wanted a good picture, who unfortunately got a little too close. And then there was one death on completely the other side of the ocean in Papua, in the Indonesian part of New Guinea.
That's these transocean tsunamis, which are incredibly dangerous. What about Hawaii? Can it generate its own tsunamis?
Yes, we have big earthquakes in Hawaii because we have big volcanoes, and the volcanoes are very, very large, very heavy, but weak.
Yeah.
And they're constantly sort of collapsing and oozing out sideways, but they're also being pushed. They have rift zones which fill up with magma and then exert a strong outward pressure. So every once in a while, the whole side of the volcano will slip outwards about 30 feet, and there's ocean in the way, so the ocean gets pushed out of the way.
And presumably that doesn't give you much of a warning to issue if it's so local.
That's right. The water around the Hawaiian Islands is deep, so that means the tsunami travels very fast. The last time something like this happened was 1975. The epicenter actually was right at this spot. At that time, it took us an hour to get a warning out. Now we're down to 3 minutes.
How about those subduction zone earthquake tsunamis, though? I mean, how much warning do you get for those? And what do you do to warn people to get off the beaches?
For Hawaii, there are sirens, and if we decide an earthquake provides a tsunamigenic hazard, then we just go off on the blower and say, all counties sound your sirens, and without question they just push the button and the sirens immediately start blowing.
And people react accordingly, do they?
Well, people on the Big Island certainly will, because they have felt the shaking.
Yeah.
On the other islands they've probably felt shaking, but fortunately the sequence of events that has happened in the recent past, everyone is educated. They know what to do.
Well, Hawaii sits right in the middle of a plate, but it's along the edges of plates where most of the geological action occurs. So we sent Kate off to Iceland, where 2 plates meet.
From above, it's clear that Iceland's landscape is scarred with great cracks and fissures, as if it's been ripped apart like paper. Some cracks are several miles long, and added together, they form a huge rift which crosses the entire country. For millions of years, the North American plate has been drifting westwards, while the Eurasian plate has been creeping to the east, like 2 enormous conveyor belts moving in opposite directions. These tectonic forces are tearing Iceland apart, and the results of this monumental tug-of-war are clearly visible in the landscape. As the plates pull apart, magma rises from the Earth's mantle to fill the gap. So wherever there are cracks in the crust, there are volcanoes too, great long lines of them running along the central rift. I've come to southwest Iceland to find out more about these great tectonic features. For scientists like Bjorn Oddsson, studying active volcanoes can be a dangerous job. But here, there's a unique opportunity not just to get close to a volcano, but to go right inside one. We're joining a team of mountaineers who are making final preparations for an extraordinary descent, a real-life journey to the centre of the Earth. They've rigged up a mechanical lift, which will lower us directly into what was once the fiery mouth of this volcano. It's a first for both of us, and I, for one, am slightly apprehensive. Are you a little bit nervous about this slightly Heath Robinson piece of kit that we're descending into the bowels of the Earth in?
I think it will work.
I hope so.
I hope so too.
Crossing the gantry to the lift feels a bit like walking the plank, and the gaping hole beneath is impossible to ignore. But at last, we're ready to descend. Okay, we're getting into a very narrow bit here. It's a strange feeling, being slowly swallowed up by the mouth of a volcano. It's a very kind of organic feeling space, this, isn't it?
Yes.
It feels almost alive, the kind of shapes of the rock.
It's just like it happened yesterday.
Yeah, you can see the bits of magma kind of left on the side of the chamber.
When it was plastered on the wall, it was not fully solidified.
So these sort of chocolate-like drips stuck to the walls, that's the magma, that's the remnants of the magma?
Yes, that's the remnants. Gravity pulls it down and forms these candle-like forms and freezes.
That's incredible. As we descend further, the tube widens out and we lose sight of the walls. We're lowered into a vast, open chamber. From top to bottom, it's 150 metres, taller than St Paul's Cathedral. Powerful lights help to reveal the huge space, which is truly an incredible sight. I'll tell you what's so extraordinary that I really wasn't expecting was the colour. It's just a riot of every colour you can think of.
That's due to many reasons, and Iceland and Icelandic mountains, they are built up with many lava layers and many events of volcanic eruption. And we see both ash and lava from different types of volcanic eruptions. So this is like an open book. You can read the story of this mountain.
The red and orange rocks down here are all old lava flows from different periods in the history of this fissure. As lava flowed to the surface, layer after layer built up to create the mass of the volcano above our heads. In the damp air of the cave, chemical reactions have changed the colour of the rocks in those old lava flows, like the rust on a piece of iron. But as well as a beautiful sight, it's important to remember the significance of this huge crack in the earth. We're not only exploring the bowels of a volcano, this place is part of a much bigger system.
Most volcanic eruptions in Iceland are on fissures. So Iceland is pulled apart. So this is the center, and on the one side we see North American plate, on the other side we see the Eurasian plate.
So we're sort of standing in the middle of those two tectonic plates?
Yes, of these two continents.
Does that mean effectively what we're doing is standing in a kind of no man's land between the two?
We are in Iceland.
Good answer. it's hard to predict which part of Iceland's rift will open up next. But by studying these active zones, not only on the surface, but now also within the fissure itself, Bjorn and his team stand to learn much more about how Iceland's tectonic forces give birth to volcanic activity.
When I realised you were going to do that, I thought, she's just going to get into a big black hole you can't see in, but just looking at that film.
You have gone slightly green.
Well, I just didn't think it was going to be like you said in it.
Oh, well, it was an incredible experience. It was an absolutely incredible experience, and it was just a really great way to understand that formation of Iceland. So, you know, if we just run through it again, you've got your North American plate and your Eurasian plate. Will you be my plume?
Yes, yes. So you've got
so you've got the plume coming up, and that plume is basically creating Iceland.
Just there.
But what's really interesting is it was the exact same process that also helped create some of the features that we love in Britain. Because if we do it again, our North American, this is the UK.
So, exactly, so that's North America, that's the UK. If you go back 55 million years ago, you don't have an Iceland, you don't even have a North Atlantic Ocean, because that starts to open up. There's a plume that comes out.
So that's pushing those two apart.
It breaks the continent apart. You get a chain of volcanic centres. So you've got volcanoes that are in Arran, in Mull, in Skye. It's spewing out lava that you get, the Giant's Causeway is one, and also Fingal's Cave, Staffa. And then what happens, of course, is that plume kind of breaks it up, creates a new ocean, and the ocean just drifts apart. So that today, you know, North America's here, Britain's here, and the plume's still coming up here. And that's where Iceland is.
So could then you get to a point where Iceland stops effectively being the grout between the two plates, and that then gets forced apart, and you get sort of ice and land?
Yeah, I guess. I mean, I think what will happen is if the plume starts to be less dynamic, and then what will happen is there'll be less material coming out, and you'll get a east and west Iceland that drift away,
drifts apart. But then Hawaii is a bit of an anomaly then. I said it, I can never say anomaly. Because it's not on a plate boundary, is it?
No, but it is on a moving plate. And one of the issues here is you've got a one plate and you've got a plume rising up, and that plate is moving. So what happens, we've actually got a graphic that's going to explain it, but what happens, the plume comes up, there it is, and it punches its way through, and it creates this volcanic island. But that, because it's on the moving plate, that then carries itself northwestwards on this almost like a conveyor belt, and then the magma's still coming up from depth.
It's still coming up, so another new island then
just goes
pops
straight up, creating a new island. There we go.
So that's exactly why, when you look at the Hawaiian archipelago, it is a line of islands.
Yeah, no, absolutely. And it looks like one of these kind of, you check out a supermarket, the whole set of things coming past, a whole series of volcanic islands. Now, eventually, you know, what we'll actually get there is there'll be a new island. Hawaii will become inactive, it will drift off to the north.
So the one we're standing on will drift north.
Yeah, and we're actually getting a new island. The new Hawaii is over there. So about 22 miles offshore, there's an island called Loihi, which is only 1,000 metres, 3,000 feet below sea level. It's rising up. So if anyone in Kalapana really wants new land, hang around for a few tens of thousands of years and occupy that when it pops up.
Fascinating stuff. Well, the lava plume below Hawaii doesn't just create volcanoes and new islands. It moves the Earth in a way that scientists at the Hawaiian Volcano Observatory have to be very busy indeed.
My name is Weston Thielen. I'm the Seismic Network Manager here at the Hawaiian Volcano Observatory. I study specifically earthquakes that occur on volcanoes. Obviously, we've got a very active volcano setting here. We have Kilauea that's active and has been active for several decades. We've got Mauna Loa that isn't currently erupting but has a long history of very frequent eruptions. And so by recording earthquakes, we can start to understand some of the processes that are going on under the volcanoes. Specifically, we can start to forecast eruptions and when they might happen. What's really, really fun is when you find something out about the volcano that you didn't know before. And that's what I think I live for, and that's what a lot of the scientists around here live for. Earthquakes that occur under volcanoes come from many different sources. Fundamentally, you have magma moving up from deep to the shallow part of the crust. And as it moves up, it uses fractures that are already existing in the crust. And those cracks or fractures have walls on them that vibrate. And those walls vibrate much like a piano string does. And that creates low-frequency earthquakes that we see and we typically look for before a volcanic eruption. So here we have a seismometer. And essentially all a seismometer is made out of is a magnet. And that magnet lies within a coil. When an earthquake passes by the station, the seismometer here records that ground motion as a voltage, which is then being sent back to the digitizer and the electronics box behind us. Around the island of Hawaii, we have somewhere on the order of 70 stations. And we need a network in order to record those so that we can surround the earthquake and we can triangulate and locate the earthquake and figure out how big it is. In 2011, the Komomoa eruption, we saw an increase in earthquakes and in tremor. What you can see is at the beginning, where we didn't have the eruption, we have flat traces. There's no earthquakes. As we move into the eruption, you can see that the earthquakes, these vertical lines here, are increasing quite dramatically. And as they do, that's an indication that magma is on the move up to the shallow part of the crust. And the location of these earthquakes tells us essentially where that magma is moving from and to. That's kind of one of the reasons why we all got into this field, was to look for eruptions, study eruptions, forecast eruptions, to figure out what's going on.
Okay. Well, it's that connection between earthquakes and volcanoes that actually leads us to our very first viewer's question. You got in touch with us via bbc.co.uk/volcanoes. Now, I know some of you are going to be shouting at the telly saying, it's not working. Unfortunately, yes, at the moment our website is down, but the techie whiz kids are doing everything they can to get it back up and running. So where did I do? Oh, here we are. This is our first question. It came from Paul Metcalf, and actually a lot of other people clearly worried about their summer holidays. El Hierro.
Canary Islands, yeah.
Exactly, in the Canary Islands. There have been numerous quakes, and the island has apparently, according to Paul, risen by 9 centimetres. Does that mean it's going to erupt?
Well, this has been going on since late last year, actually, when some UK volcanologists predicted there was going to be renewed activity on this place. And it has had quite a lot of activity, but just in the last few weeks, it's calmed down a little bit. So that's why it's not on our map. It's not really been doing very much. But the point is, this is one, it's our closest active volcano. A lot of people go there on holiday, so this is one we'll definitely be watching.
But is it a common occurrence that volcanoes look like they're about to kind of build up to an enormous eruption, and then it just all sort of fades away?
It's one of the frontiers of we can tell when the magma's coming up, but what it's actually going to do when it gets really close, is it going to burst out or is it just going to sink back down? That's a tricky one.
Okay, which leads us to another question, slightly connected to all the things we've just been talking about. We know why we don't have volcanic eruptions in Britain, but we do have earthquakes. Why is that?
We do. I mean, we're sitting in the middle of a plate in Britain between Iceland and between Italy, the two places we've been doing our film. So we're quite passive, but we have got lots of fault lines, ancient lines of weakness, because we used to be right at plate boundaries, like 50 odd million years ago. So those fault lines are places where stress builds up and it gets released in earthquakes, but they're very small. So the biggest earthquake we've seen today, 5.2 in Papua New Guinea, that would be one of our biggest ever earthquakes. So we got to keep things in perspective.
We've had a lovely question in from Katri Headley. She is 6. Thank you, Katri, for getting in touch. She wants to know why lava is red.
Why lava's red? That is a very good question. Well, lava's red because as you heat something up, it gives out more energy, gives out light energy, and you can see it. So if you want to see that, you can go to your oven with your mum there, and she can turn on the hob, and you'll see it start to go red if you've got that kind of oven.
So that's why when we've got cool lava, it's black.
It's black.
And when you see it, particularly at night, you get that wonderful red glow. There you are, Katri. I hope that answers your question. Owen, age 10, has got a really tough
These
one.
are all the hard ones for the youngsters, isn't
And
it?
now Owen is going to be here in 2 weeks, so you can come and visit some of the places that we've been to, Owen. He wants to know why craters are almost always round.
Yeah. That's because they're explosive. They're explosive in one or two ways. They're either from magma coming up and exploding out, so all the energy radiates out in all directions, round crater, or it's because the magma comes up, explodes out, and then the thing collapses in. And again, same thing.
So you
collapses
get that
on
kind
itself.
of
broadly round, yeah.
Okay. And I think we've got time for just one more. And this one has come in from Mrs. Bell's Year 10 geography students. Mrs. Bell teaches at the Acle High School in Norfolk. And I love this question. She says, why, or they all say, why are volcanoes called volcanoes?
It goes back to the Roman times, actually, because there's a lovely volcano in the Aeolian Islands in Italy, and it's perfect cone shape, and it's called Volcano. And it's because that's where they thought the god Vulcan was. And so we've kind of stolen it from Italy, really.
So sort of someone saying, oh, we can have one of those. We've got one of those volcans. So you don't all need to go to Italy.
Exported. It's an export. It's sent all the way around the world.
Thank you very much indeed for all your questions. Tomorrow is our last show, but once the website is up and running, you can keep them coming in, and you can also tweet them on #VolcanoLive. Now, it is a constant frustration for volcanologists that they can't go deep inside a volcano to collect the material that would tell them all the answers to their questions about their mysterious inner workings. But John Blundy, who works at the University of Bristol, has discovered that there's a particular sort of rock that could answer the questions that keep him awake at night. He went to the Caribbean to try and find them.
As an igneous petrologist, someone who looks at molten rocks, I work on the products of volcanic eruptions, and I interrogate them to find out something about what happened before they came out of the ground. A bit like a pathologist working with cadavers. I find rocks really fascinating. There's something about them that's really tantalizing because it's like a little puzzle that Mother Nature's thrown up. And the challenge is to try and unpick the rocks, to decipher the clues as to how they formed. Every year I go with colleagues from Bristol University to do fieldwork in the Caribbean. In spring this year we went to the island of Dominica, which is a lush tropical rainforest. There are 9 active volcanoes on Dominica, none of them terribly well studied, and there hasn't been a really big eruption for about 1,500 years. In the last year or so, there have been a number of shallow earthquakes under the north of the island, beneath a volcanic centre called Morno Diablo. And the real objective is to try and understand a little bit more about what goes on under Morno Diablo, so that we can try and understand these earthquakes. We're here at the northern end of the island of Dominica. I'm looking out over the rather splendid volcanic peak of Morno Diablo. If I was living in any of these little coastal villages here, or even in Portsmouth, beautiful harbour to our left, I'd want to know a bit more about Morno Diablo. So we set out to look for some samples along the flanks of the volcano. The rocks we sample are like the witnesses to an event. In this case, the event is a volcanic eruption. And just as your detectives want to find the best possible witnesses, we want to find the best possible rocks.
Have you got any orthopyroxene in there?
Brown orthopyroxene, hornblende cleavage really clear. This is a great sample. Sometimes, if you're really lucky, the volcano throws up bits of its guts. This is a cumulate. A cumulate is, as its name suggests, an accumulation of crystals that have been deposited from magmas underground. And the remarkable thing is that each cumulate represents a discrete moment in the evolution of the volcano. Within these cumulates, there are clues to the past history of the volcano. They're not very common. In some ways, it's a bit like sieving for gold or looking for diamonds. It's rewarding if you find some, frustrating if you don't.
It's all streaky grey altered.
First couple of days on Dominica, we didn't find any cumulates at all. I'm not a pumice picker. I'm a pumice picker's son. We were also looking for volcanic rocks themselves, especially pumice and lava. Here's a bit of pumice. It's a bubbly, air-filled rock. The bubbles were where there was once volcanic gas. And it's that volcanic gas that expands and pushes the magma out of the volcano. And this would have come out of a volcanic vent at close to the speed of sound. The pumices themselves contain crystals.
It's really the little white pumices we want. I'm hoping these are reasonably fresh.
And the compositions of the crystals can give us clues as to where the magma was stored before the eruption, which in turn tells us where we ought to be looking for signs of unrest before future volcanic eruptions. Day 3, we were now starting to feel a little bit despondent about our failure to find any cumulates. We got a little bit of intelligence that there had been a dam break a few years ago. A natural dam had broken through and dumped an enormous volume of material from the volcanic centres into the Laiu River. So we set out to see what we might find.
Have I got a goodie for you?
Oh yes, what have you got?
Oh, yes!
The river was flanked on either side by huge banks of gravel, and because of the action of water winnowing out a lot of the finer stuff, these gravel deposits were unusually rich in cumulates.
Perfect.
It was a cumulate bonanza.
Wow. This volcano really did spew its guts up.
It's exciting because it comes at the end of a couple of days of frustration, a couple of days of thinking that perhaps it's not going to work out on Dominica as it's worked out on other islands.
This is without a doubt the most involved cumulate we've come across.
I tell you, Dominique is the place to be.
Dominique is the place. Well, this is just a perfect spot for collecting these things.
The work we do will ultimately contribute to a better understanding of these volcanoes. I think volcanologists have a societal responsibility to do the best they can to understand restless volcanoes, because only through that understanding can we be in a better position to anticipate and mitigate volcanic hazards and potentially save lives of people living in the shadow of volcanoes. That material from Dominica alone will sustain a research effort for a good few years to come. And they're really nice looking rocks as well.
Now I've got one of John's rocks here. It is lovely. It's just great to think that this is like a wee forensic time capsule that allows us to go both back into the, into the depths and also back in time. And just a kind of a call up really, because John Blundy will actually be manning our weblog tomorrow night. So save up all your really difficult questions for him. And if you just get buzzed here by some of the things like that. But if you want to get that, it's www.co.uk. It's not currently on there at the moment, but keep trying, it's going to get there.
It will get there. Now it is extraordinary really that what we've uncovered in the last hour is the fact that science knows the planet quite well. We know where the tectonic plates are, the volcanoes, where we're most likely to get earthquakes, and yet you look at communities like this, you look at Kalapana, and you can't help sort of celebrating the human spirit, that human beings do want to live in places like this.
Yeah, I mean, the first thing is this stuff is the way the planet works. We've got to get used to it. The thing is, people will do it for all sorts of reasons, for that kind of frontier spirit, but also that human nature, not being cowed by the volcano.
No, absolutely. Well, it's our last programme tomorrow, but we've got lots of treats in store, haven't we?
Yeah, tomorrow I go to Italy to go face to face with the 2,000-year-old victims of Vesuvius.
An amazing story that. Ed Byrne creates a supervolcano with just some plastic balls and a rubbish bin.
And we go to the ends of the earth, to Antarctica, to get the perfect volcano.
So we will look forward to seeing you tomorrow night at 8 o'clock. We'll be back at our lovely crater. See you then. Goodbye.